Okay, in this video I want to go through how to differentiate functions of the type when you have sine of some function or cos of some function. And this just is another exercise in using the chain rule. So let's say we have y equals something like sine of, let's say, 3x plus 5. Now we know how to differentiate sine x, but what if we have sine of another function? So as usual, so this one, once again, we use the chain rule. And as with the cases of things like e to the power x and ln x, I'll show you the detailed working and then show you how to do it in a quick method as well. So first we take the, whatever is inside this bracket here, whatever the angle of this sine function is, make that your t substitution. So let t equals 3x plus 5. Now if t is equal to 3x plus 5, then y should be equal to the sine of t. So instead of 3x plus 5, I just put in t. Then we take dt over dx, so differentiating this function, I get 3 dy over dt will be equal to differentiating sine. We know the derivative of sine x is equal to cos x, so the derivative of sine t will be cos t. And then we just apply the chain rule, so we say dy over dx is equal to dy over dt times dt over dx. So dy over dt, that's equal to cos of t times dt over dx, which is equal to 3. And the final step is to just put back 3x plus 5 instead of t. So I'll bring the 3 to the front, so I can write this as 3 times cos of 3x plus 5. And that is the derivative of sine 3x plus 5. And before giving the short method, I'll just take one more example. So let's say we have y equals sine of, let's say, 3x squared plus 6x. So once again, your 3x squared plus 6x will be your t substitution. So use t equals 3x squared plus 6x. And that would give y is equal to sine of t. So in this case, dt over dx will be equal to, differentiating this function, I get 6x plus 6 dy over dt will be equal to cos of t. And then when you apply the chain rule, we have dy over dx is equal to dy over dt, that is cos t, times dt over dx, and I'll put that up front here, so I have 6x plus 6. And then the last step is to substitute back for t, so we have 6x plus 6 times the cos of 3x squared plus 6x. Okay, so I think what you probably noticed is that I always get the derivative of this inside part in my final answer, and then instead of sine, I get cos, because the derivative of sine is cos. I get cos of whatever that angle was. So if you try to write the general case, so if I take y equals sine of fx, so if I just take the equation y equals sine of some function of x, then dy over d, so what we do is we make this our t substitution. So we say let t equal to f of x, so that makes y equal to the sine of t. So dt over dx, we saw this in the previous videos when we did e to the power x and ln x. So the derivative of fx, I write that as f dash of x, and dy over dt will be equal to cos of t. And then using the chain rule, I get dy over dx is equal to cos t times f dash of x. So I'll write that, so that's dy over dt times dt over dx. So I get f dash x times cos t, but instead of t, I'll just put in f of x. Okay, so what the rule says is if I have sine of some function, then first find the derivative of whatever that function is, derivative of what the inside part is. So that's f dash of x, and then multiply it by the cos of whatever that function is. So let's take an example. So let's say we have y equals sine of, let's say, 3x squared plus 5, and we want to differentiate this. So dy over dx. Now the way I think of it is that instead of 3x squared plus 5, just think of this as sine of x. Now if I have sine of x, then the derivative is cos of x, so I get cos of x, but instead of x I have some function. So I get cos of 3x squared plus 5, and then I got to multiply that by the derivative of whatever this inside part is, whatever this angle is. So the derivative of 3x squared plus 5, that is equal to 6x. So I get 6x cos 3x squared plus 5. Now, although I've only shown this for sine of fx, the same applies for all other trigonometric functions. So let's say if I have y equals cos of, let's say 6x plus 9. Now dy over dx for this is going to be, so once again treat the cos of 6x plus 9 as cos of x. So what's the derivative of cos of x? So the derivative of cos is minus sine. So I'll get minus sine, but instead of x I have some function here. So I get minus sine 6x plus 9, and then I got to multiply that by the derivative of the inside part. So that is equal to 6. So what I get is minus 6 sine 6x plus 9. Okay, we can also try one with the tan function. So the same rule applies for tan as well. If I have y equals, let's say, tan of, say, 6x cubed. Now the derivative of tan x, if I differentiate tan x from your formula booklet, you can check this, you get sec squared of x. So in this case, dy over dx will be equal to sec squared of, but in this case it's not sec squared of x, it's sec squared of whatever that function is. So sec squared of 6x cubed, but then I got to multiply it by the derivative of this, whatever that function is. So the derivative of 6x cubed, that gives 18x squared, sec squared 6x cubed. So these aren't too difficult once you actually spot the pattern. So let's take one with, let's say, what are those? We've taken sine, cos, and tan. So let's take one with sec x as well. So let's do sec of, let's say, 6x plus 12x squared. Okay, now what's the derivative of sec x? If you differentiate sec x, you see that we get sec x tan x. So that's just differentiating sec x, you get sec x tan x. Now in this case, you're not differentiating sec x, you're differentiating sec of this function. So dy over dx will be equal to sec of that function. So I have 6x plus 12x squared. Then I got tan of that function. So tan of 6x plus 12x squared. Now I've got to multiply all of this, but by whatever the derivative of this function is. So that would be equal to 6 plus 24x. Okay, and I hope it's clear what I've done here. So instead of writing sec x tan x, so I have sec and tan of whatever that function is times the derivative of that function. And if you think this method is too tricky for you, you can always make the substitution t equals 6x plus 12x squared, and you'll see that you get this answer. And then I'll do one with the cot function as well, or perhaps only the cosec function. So let's do y equals cosec of, shall we say, just take something simple. So let's take 12x. So the derivative of cosec x is minus cosec x cot x. So I have minus cosec x cot x. But in this case, I don't just have an x, I have 12x. And then I got to multiply that by the derivative of this inside part. So the derivative of 12x is equal to 12. So I get minus 12 cosec x 12x cot 12x. Okay, and then let's just, for completeness, do the cot x as well. So let's take y equals cot of, I'll take 6x plus, let's say 5x squared. Okay, the derivative of cot x is minus cosec squared x. So dy over dx will be equal to, I'm going to get minus cosec squared of whatever this function is. So instead of x, I put 6x plus 5x squared. And then I got to multiply this by the derivative of the inside part. So the derivative of the inside part will be 6 plus 10x. And for all these examples, if you think doing it in one step is too much to begin with, then always make the substitution that t is equal to whatever is inside this bracket, and then you can work it out in more detail.